Rolling. Thank you for recording, Ryan. I'm going to give a quick introduction. So this week we had the pleasure of welcoming Dr. Talea Mayo to our fall virtual seminar series. Dr. Mayo is a computational mathematician with expertise in the development and application of numerical hydrodynamic models for coastal hazards. She earned her Bachelor of Science in Mathematics from Grambling State University and her Master's and PhD in Computational and Applied Mathematics from the University of Texas, Austin. Since graduating, Dr. Mayo has spent time just down the road from us at Princeton University and at the University of Central Florida before taking her current position at Emory University, where she is an assistant professor in the Department of Mathematics. Dr. Mayo has been the recipient of several prestigious awards, including the National Center for Atmospheric Research Early Career Faculty Innovator Award, the University of Central Florida Teaching Incentive Program Award, and the National Academies of Sciences Gulf Research Program Early Career Research Fellowship, amongst others. So without further ado, I will pass it over to Dr. Mayo.
Thanks, Jackie. Can everyone hear me? Okay, cool. So I'm super excited to chat with you all today. I really enjoyed some of the meetings that we had already. And I wanted to make it clear that it's pretty difficult for me to schedule a full day of things because we have a newborn, but if you're interested in following up or scheduling a meeting over the next few weeks or whenever, please just send me an email and I'd be happy to meet with you. So today I'll chat with you about climate change impacts on hurricane storm surge risk. And so I know that a number of people here are interested in data assimilation, and that's actually not what I've been working on most recently, so I'm not talking about it here. But again, if you want to chat more about that, we can definitely set something up. Sure. Okay, so a brief outline, I'll give a short description of hurricane storm surges and kind of their impact and why they're so important. I'll discuss hydrodynamic modeling and how we model them, and then I'll discuss two projects I've worked on understanding kind of the climate change impacts on storm surges. So hurricane storm surges are a natural hazard that affects coastal regions. And so I always like to kind of present coastal regions and why they're so interesting. I know some of you all do physical oceanography, but I am mostly interested in the coastal environment. And I define this as the intersection of complex physical processes and the built environment. So I spent the last two departments I was in were civil engineering departments. And so coastal regions kind of are made up of the interesting aspects of that. So they're also home to more than 40% of the US population, and this is growing. So by 2060, it's expected that coastal populations will increase by more than 50%. Unfortunately, coastal regions are also at an increasing risk of natural hazards. And so the two that I've spent the most time studying are floods and coastal erosion. So I'll be talking about coastal flooding today, but then we've also done some work understanding kind of erosion modeling and how do those flood impact the shoreline. So specifically, hurricane storm surges are defined as the abnormal rise of water generated by a storm. So if we consider kind of the normal high tide, then we're talking what's above and beyond that due to a hurricane approaching land. Usually, if we're discussing the total water level, so the amount of the tide plus the storm surge due to the hurricane, then that's referred to as storm tide, but you'll hear people use them interchangeably. So if we talk about like a surge that occurs at high tide, then that's the storm tide. I think most simplistically, it's easy to think about storm surge as kind of a fight between the surface wind stress pushing towards the shore and then bottom stress trying to hold everything in place. So some of my earlier publications are kind of specifically addressing these two things. Unfortunately, they are the greatest threat to life and property from hurricanes. And Katrina, which is the storm that really got me interested in hurricanes and storm surges, caused maximum surges of 27 feet. And then I know that you all were pretty directly impacted by Ida. And so the max surges, their preliminary estimates are 8 to 10 feet. So surges have become, they are very important. And so a lot of attention has shifted to communicating the storm surge hazard. So you're probably used to hearing as a storm approaches landfall, it's expected to be category 3, 4, 5. And so that's describing the maximum wind speeds of a hurricane. But in the last decade or so, or especially since Katrina, there's been like a concentrated effort to really communicate the storm surge risk as a storm approaches landfall too. So this is an image from Hurricane Katrina, which, as I said, is the storm that really got me into this area. I was living in northern Louisiana when it struck the Gulf Coast. And so it didn't impact where I was directly at all because of the shift in the track after landfall. But most of the peers around me, I was in college, were from the Gulf Coast. So that was really my first interaction with a hurricane and understanding kind of the devastation that it can cause. This image is from Hurricane Sandy, which hit the Northeast coast right before I moved to Princeton. And so this storm was particularly devastating because of the high population density and I guess civil infrastructure that it impacted in the New Jersey and New York regions. And then I should update this last figure, but this figure is from Hurricane Harvey, which impacted the metropolitan Houston area. And so it was mostly a rainfall event. Hurricane Harvey kind of stalled over Houston and just poured rain. But one of the interesting things is that the surge in the Gulf of Mexico caused Galveston Bay to rise. So a lot of the freshwater flooding or the rainfall couldn't drain the way it was supposed to. Another interesting thing about Harvey is that a lot of the civil infrastructure right in the coastline, so the amount of building they had done at the expense of like destroying kind of the natural features of the area, reduced the bottom friction, as we would call it. And so that allowed the surge to propagate much further than it might have otherwise. So when we're trying to model and understand hurricane storm surges, the models that I use what are called the shallow water equations. So these have conservation of mass and conservation of momentum. And then you can solve the set of PDEs for H, which is the total height of the water column. So this is the like ocean floor, and then this is the water surface. And so H would be this total height. And you can solve for this and then also currents. So most of the applications I use tend to focus on H, the total height of the water column. These PDEs are obviously too difficult to be solved by hand, especially because you have forcing terms usually impacting the surface roughness. So that's the part that's coming from the hurricane that allows us to understand what does the height of the water column look like for a given place. So for this, we use computational models. The two models that I use the most are called SLOSH and ADCIRC. So this is an image off the ADCIRC website. And what you're looking at is kind of the outline of North America. So this is Florida, if you can see it. And then these are the Carolinas, and then the Northeast region. So there's Massachusetts. And so what we do is we discretize the shallow water using triangular elements and then solve it with a finite element method. And I guess what's most interesting, or like the reason that this method is so important, is because we use finite elements, and that allows the discretization to be non-uniform or unstructured. And so what that means is that we can have a kind of coarser resolution in the areas that we don't care so much about. And then we can increase the resolution as we approach the shore. And for our applications, that is what we really care about. So that's saves us computational time because we don't have to solve the shallow water equations as many places just to get high resolution near the coast. The other model that I've used is called the Sea Lake. It's the slosh model, the Sea Lake and Overland Surges from Hurricanes model. And so this model is the official model of the National Hurricane Center. It runs super fast, and so it uses finite differences to discretize the meshes. And so you are kind of bound to this uniform mesh, uniform grids, where everything has to have the same spatial resolution. But we get away with having more resolution inland by using polar coordinates. So if you think of like a radii and how things are smaller near the center of a pole, then that's kind of what's happening here. So these elements in near the pole of the mesh are finer than away from the mesh. And so slosh, even though it uses structured meshes, still can give you resolution that you need close to the coastline, and it runs very, very fast, which, as I'll state in a minute, is really useful for some applications. So there's kind of these standardized meshes all along the US coastline. And that's another reason that this model is kind of easier to use. It's kind of designed in a way that it can be used kind of out the box, as opposed to AdCirc. You kind of have to get your hands on or develop the mesh yourself, which can be good because you can get resolution where you need it, but it's also not something that you can use easily right away. So hydrodynamic models are used to forecast storm surges during hurricanes, and specifically they can be used to guide emergency management and response. So this is an image from the Sierra website, and so this website kind of showcases what the AdCirc model is showing predicted storm surge based on the predicted meteorology or the hurricane forecast. And so they'll take NHC date forecast, National Hurricane Center forecast of a storm, and then use that to determine then what should the storm surge forecast be based on AdCirc. But I guess something similar that happens is with the slosh model. So some of those advisories I showed a few slides back are produced in the same way. So using the latest forecast guidance, using the slosh model, what is slosh saying is most likely to occur in terms of storm surge. And so that's useful for emergency response. So if a hurricane is approaching landfall and you're in charge of a community or a city, you want to know what's going to happen, then it's useful to have these type of models. But one thing that we need to be thinking about is how do we really prepare for extreme events that seem to be occurring more regularly? So it's becoming kind of intractable, or I guess as a hurricane is approaching landfall, kind of the best you can do at that late in the game is evacuate if it's going to be really bad. But if these events are occurring more and more frequently, then there's preventative measures we can take to be better prepared for those events before they occur. And so the question is how, and how do we use modeling to do this? So this is a question of coastal resilience. And so I worked while I was in Princeton on a project where this was the exact need that we were trying to address. How do we prepare communities for these hazards? And so there's a number of approaches that we can take, and they're multidisciplinary. So some of the measures, for example, natural measures, that means just finding a way to preserve natural things that are already there that naturally reduce the amount of storm surge risk. So an example would be like marshes and wetlands naturally dampen storm surges. And so we want to find ways to make sure we're preserving what's there as opposed to maybe like building over them. Nature-based solutions for coastal resilience might include building things that aren't naturally there, but are nature-based or reflect nature. And then we have structural approaches, which tend to be what at least engineers think about when we're thinking about resilience. So do you build a flood wall? Do we want to implement dune, or do we want to build a seawall or something like that that can physically just keep stormwaters out? And then finally, there's also non-structural approaches. And so you might think of that as like policy recommendations or infrastructure or insurance pricing that I guess incentivizes people to either move away or at least financially be prepared for disaster. So true coastal resilience requires long-term planning and risk assessment. So in other words, we have to do more than just kind of model what's going to happen every time a hurricane appears. So for long-term risk assessment, the methods that I use, I refer to as probabilistic risk assessment. And so the approach that we're taking is extreme value analysis. And so I just want to take a minute to explain, like, what does that look like? So if you have a large sample of events, so here I have maximum storm surges from maybe 2,000 to 3,000 hurricanes. First of all, what we're most interested in is kind of the tail end of this distribution. So usually when we're interested in information, we kind of want to know naturally what occurs the most often. So we're interested in kind of the modes. But in this case, in risk assessment, we really want to know about the extremes. So it's not enough to be prepared for, the everyday rainfall. We really want to be prepared for something that doesn't happen very often, but that is really impactful and important when it does happen. And so I call these low frequency, high impact events. So here, I'm kind of outlining this tail of the distribution as opposed to kind of the more common values that we might see. And so what we can do is model that tail using different distribution. And so in this work, we use the generalized Pareto distributions. So if we define this large threshold U, so in this example, it's 2 meters of storm surge, then we really want to model for everything that happens that's greater than that, assuming like that's where we really need to put the dollars and resources. And so if we have enough data, what we can do is fit the rest of the data in a way that gives us this distribution. So there's like packages even in MATLAB and R. So this is a method that's just fitting extremes. So you'll define what do you call extreme, and then you can calculate empirically what's the probability, what's the chance that you're even out here, and then use the model to kind of fit the shape and the scale of that data. And so once you have those parameters, you can manipulate them in a way, wait for the to go away, that will produce a return curve. So that's what you're seeing here. At the bottom, you're finding a function for H, which is a return level. And so if you define or plot what does this function look like for a range of H, then you get what's known as this return level. This is return period, sorry, and this is return level. So in case you're unfamiliar, I also want to take a second to explain, like, how do you read a return curve? So probably, or maybe you've encountered the term like 100-year flood. And so the return curve is what's going to define those values. So in this figure, the 100-year flood is something like 3.5 meters, and then the 500-year flood is 4 meters. And so these flood levels are what is often used to inform kind of long-term risk strategies. What a return period actually is it's a measure of the probability that a certain level is exceeded. So for example, the 100-year storm surge has a 1 in 100, so the 100 is there, or 1% chance of exceedance each year. And then similarly, the 500-year storm surge would have a 1 in 500 chance of exceedance each year. So kind of the higher this return level, then the lower probability we're talking, but presumably also the higher impact. And so a lot of structures are built around like the 100-year flood. Insurance is scheduled around like the 100-year flood level plus or minus some range. And then like higher impact structures, so like a hospital or places that you really need to be protected, then we add on to that. So you might build like a hospital around the 500-year flood or the 100-year flood plus like a meter or something like that. So this is how these values come up in engineering. So the problem though is that, again, what we're interested in is kind of the low frequency, high impact event. So by definition, you don't have a lot of data because it's a low frequency or low probability event. And so specifically when we're thinking about like hurricane storm surges, if you think just in a given year, how many hurricanes actually make landfall in one specific place, then it's very low probability, right? So it's, the odds of having enough data or this type of data where you could come up with a good model at a particular place are small. And then if you think about climate change, then this is even kind of harder to do because data alone isn't going to help you understand what will happen going forward, not in this way. Okay. So because of that, we used synthetic hurricanes for this first study. So we used 2,000 to 3,000 synthetic storms for a given climate scenario. So let's just keep it general for now, but let's say it's present day climate. We're going to come up with these 2,000 to 3,000 synthetic storms that are representative of present day climate. And I'll say a little bit more about that. But specifically, the storms are going to come within 200 kilometers of a site. And we're going to make sure they're at least tropical storm strength so that we're getting this type of data, right? We're bound to get some of the extremes. And so this model that generates this is not mine. It comes from Kerry Emanuel from MIT. So he's able to generate these storms, or his company generates these storms if we pick a particular site, and then also has some information about like the probability so we can scale things back down after we model them. The climate scenarios that we use are basically present day. So I'll refer to that as like the NCEP NCAR reanalysis, which was supposed to kind of capture what were the present day atmospheric dynamics or climate dynamics. And then also climate dynamics based on climate models for the end of century, given like the worst case scenario or RCP 8.5. And so we used 4 different models so we could get a feel for kind of the variation that might come from using different models. And these models kind of captured the range of things that we would see. So that's why we use those in the study. But if you had another climate model, then you could use climate data from that same climate model along with this methodology to generate the synthetic storms and then do a similar experiment. Okay, so just a little bit more about the storm data. So this is basically showing you the solid lines are showing you end of century and the dashed lines are showing you present day, and then NCEP, so the black, that's based on the observed data or the analyzed data, and then the rest are modeled. And so what I'm going to do in this presentation is just kind of compare the same model. So if you look at, for example, this is maximum wind speed. This is a distribution of those 2,000 to 3,000 storms. In this case, it's 2,000. So if you look at this blue dashed line, that's GFDL present day. So basically the distribution, there's kind of like this mode around 50 knots maximum wind speed. And you can kind of just see this shape, and this tail out here ends pretty short. So you have to take my word for it there, but it's not a long tail. So most of the extremes are at least like less than 150 knots. And then if we look at the same type of distribution for the end of century data, then that's the solid blue line. So it's the same model, but now you're seeing this shift. And so you don't look at this as if like, oh, this curve is shorter. You look at how it's shifting to the right. So we're seeing more of these higher values. That's what you're seeing here. And that's pretty much true for all of the models we looked at. I'm just going to show you GFDL data. Similarly for radius of maximum wind. So again, if we're looking at the blues, I guess here it's harder to tell, but I guess the best way again is to kind of look at the tail. So you can just see out of the sample how things are changing. So what you're seeing is there is an effect of the climate on the maximum wind speed and radius of max wind. And specifically for the max wind speeds, you're seeing kind of an intensification of the storm. There's some variability in the radius, the size of the storm. Additionally, we know coastal flooding is impacted by sea level rise. And so a lot of the literature, if you look at, especially maybe before the last few years, will focus on sea level rise being the main driver of increasing storm surge risk. So you just model the same storms on a higher sea level, and then of course you would have more flooding. And a lot of the earlier or initial studies that were looking at flood risk due to climate change, that's really all that they considered. Also, they tend to focus just on the mean sea level, so maybe local mean sea level, but just the mean. So just adding that and doing kind of like some bathtub modeling, or even if you do incorporate it into the hydrodynamics, just kind of statically raising everything and then simulating. And so one of the main goals of this study was to see like, oh, but what also will be the effect of the changing storm climatology? So by that, I mean how the storms change as far as maximum wind and size. So what we did was we estimated the distributions of the sea level rise, so not just the mean, but the full distribution. And then we could convolve it with the distributions that we computed for the storm surges. And then in the end, we get a return curve that's accounting for both. And something interesting is that this data actually comes from Rutgers, so from Rob Kopp, does a lot of sea level rise research. And so the data we used was from his set in 2014. So today I will show you results for Jamaica Bay, New York. And so this is off the south side of Long Island. But we also did the same experiments for 3 other sites, so Narragansett Bay, Atlantic City, and Norfolk. And so all of these are along the East Coast, and this was motivated by Hurricane Sandy, actually. So right when I got to Princeton, Hurricane Sandy had just happened, and so there was this question of, what kind of risk can we expect in the Northeast, since this seems to be becoming more and more common. And so these sites specifically were identified as being susceptible to inundation, but also socioeconomically vulnerable. So for this project, we partnered with landscape architects and structural engineers. And so they kind of added that aspect of picking places that, may be more vulnerable, not just because of the hazard, but just also because of the resources and the populations that were there. So just kind of some brief results for the Jamaica Bay study. If we did the methodology using the NCEP data, so this is the present day data, we call it 1990 data, we get this kind of return curve. So this is just what we get from simulating the synthetic storms and then taking those synthetic storms, pushing them through our storm surge model, and then modeling the tail of the distribution that we get. And then when we calculate the return curve based on those GPD parameters, then we get, this is what we get. So here, the 100-year flood is 3.3 meters for the present day climate. Then what we did was we convolved the distribution of the present day storm surge with the distribution for the mid-century sea level rise, and is look at how does that 100-year flood, how does the return period change? And so here what we're seeing is that the 3.3 meters that was the 100-year flood becomes the 57-year flood. And if you remember how we're defining the return period, then that basically means like the probability is changing by like a factor of 2. The chances that we'll see this each year goes from 1 out of 100 to 1 out of 57. If we add in the sea level rise from the end of century, then assuming that sea level is rising, then it's not really a surprise that it decreases even further the return period. So what was the 100-year flood becomes the 29-year flood, or what should have been a 1 in 100 or 1% chance every year is 1 out of 29. So it's almost increasing from a factor of 4 by the end of the century, just due to sea level rise. But what we know is that the climate is not just affecting sea level rise, it is affecting the storms themselves. And so that's what we really wanted to look at. And so what we do is we do the same methodology for the climate data that we've actually modeled. So in this case, the model is underestimating the current 100-year flood by 20 centimeters. So we're taking GFDL data, climate data that's representative of the present day, and then we're using synthetic storms simulated from that data So what we should have is a suite of synthetic storms that, based on the model, is representative of reality. So there's an underestimation, but that doesn't really change our effect to see, or our ability to see how it changes. How does the risk actually change if we use the same model? And so if we add on the sea level rise, but also consider how do the storms themselves change by the mid-century, then we see, again, these shifts in what is the present day 100-year storm surge. So if you remember, for the NCEP data, the 100-year storm surge was like 3.3. And then when we added sea level rise, it became the 57-year flood. So it became like twice as likely in a given year. But if we also consider the changing storm climatology, then we see this shift. So the 100-year flood shifts over here and it becomes a 34-year flood. So like 3 times as likely in a given year. And then again, if we do the same methodology for end of century, then we see the 100-year surge become the 6-year surge. So basically the point here is NCEP data, just adding sea level rise, is telling us, well, by the end of century, this risk level, which we're defining as the 100-year surge, will become something like 4 times as likely in a given year. But if we also account for how is storm climatology changing, then we see it's even more likely in a given year. So 1 out of 6. And so these are some plots just showing the return period shifts for various return periods. So the 100-year flood is here. And so what I presented was this blue line. So the 100-year flood became something like the 57-year flood, I think I said. But then when we accounted for changing storm climatology, it was the 6-year flood. And so if we use other models, we get different results, but at least you're seeing like this downward slope on each of them. So for each model is telling you that when you incorporate sea level rise, the risk is increasing, but if you account for the storm climatology, it increases more. Or in other words, you need to consider the storm climatology, or you'll underestimate what the risk might be. And then these are the other return periods. So this was the 100-year flood, but here's 50, 500, and 1,000 years. And so kind of the pattern is all the same. You see that there's kind of more variance as you're modeling what's happening for kind of the lower probability events. There's more dependence on what model, but at least like the trend seems to be the same, or I guess that's not a good thing. So unfortunately, the trend seems to be the same for all of the risk levels. And then we went a step further and kind of tried to map these spatially. So we did this kind of analysis, not just at like one specific location, but like across a stretch of coastline, and then modeled like what is the 100-year flood is 40% chance in 50 years is what this says. And so you're looking, how is it evolving over the end of the century? And so for these, we're actually just doing kind of like a linear assumptions, so assuming things are changing linear, but we have specific models for present day and end of century. And so what we're trying to demonstrate is kind of how much further inland the 100-year flood is going. And then this is the 1-year flood, and then 500 and 2,500-year floods. Then we produced maps like this for all of the locations I mentioned, and then the teams of landscape architects kind of used the data to figure out different design approaches to mitigate this risk. So this is all kind of captured very nicely in this book called Structures of Coastal Resilience. And then kind of our intermediate steps are captured on the website structureofcoastalresilience.org. And then we have a paper that's hopefully coming out that just talks about the storm surge modeling aspect part of it. So the probabilistic modeling approach that I just showed depends on synthetic storms generated from a statistical model. So that's kind of one drawback because, right, we have to be able to get these synthetic storms. That's not my area. So there's kind of like a middle step in there. And then also we're generating so many storms to have the probabilistic assessment that the computational costs to model the storm surge of each of them can be prohibitive. So the way we got around it in that study was we used the simpler model, we used slosh, and we can get information out of slosh in like a couple of minutes for one storm. But slosh is kind of coarse in different ways. So we may desire to kind of have more detail or use a better model. And so we're not able to do it with that approach. So another approach we can use is to assess the changing risk deterministically, where we're just comparing, we're doing one model run or two model runs, and then just using those runs to assess what's happening. And so that's what we did in this paper that's led by my former PhD student, Jean Camello. And that came out last year. So some details about that, we use the WRF model. So that's an atmospheric model, three-dimensional convection permitting regional climate model. It has fine resolution, so 4 kilometers horizontally and then 51 vertical layers. And I'm not an atmospheric scientist, so I just understand from our collaborators that that is a very detailed model. And I guess I should also mention that our other collaborator is Ethan Gutman. So he's at National Center for Atmospheric Research and did a bunch of modeling on the hurricane side. So specifically what was done was we modeled 21 hurricanes that were simulated under present day climate conditions. And then we added this climate change signal that again came from RCP 8.5 on the boundary conditions. So for those same hurricanes, we're implementing a climate change signal to the boundary conditions based on changes that would happen to wind speeds, sea level pressure, air temperature, humidity, and et cetera. And so those details are in this paper. And so that's our collaborator, Ethan Gutman. And so that paper is entirely about how the hurricanes would change from present day to end of century based on implementing this climate change signal. So at the end of this paper, he basically had a set of storms as they occurred or as they are supposed to reflect how they occurred. There's some variation between what was modeled and observed, and then the same storms as they would be at the end of century if we account for these things. And so he goes into detail about kind of what were the changes that these changes produced in like maximum wind speeds or radius of maximum wind, et cetera. So once we have those hurricanes, then we're again able to push them through a storm surge model. And so here, because we're really just doing 42 simulations, then it's feasible to use a higher fidelity model like ADCIRC. We use a mesh, a standardized mesh, which is called HSOFS. And so basically what's special about this mesh is it's relatively high resolution. So it has 1.8 million vertices. So that's the number, the points on the triangles where we're solving the shallow water equations, and 3.6 elements. And then it also has overland grid resolution. So not only are we able to capture kind of what's happening in the coastal ocean, which is kind of normally what ADCIRC does, this mesh was designed to go overland so we can also see what's happening on land. And then the resolution is pretty good over land, ranging from 150 to 500 meters. And so this is just a result from one of the simulations. So this is for Hurricane Ike, but we did all 21 storms. And so just kind of some quick and dirty metrics are the inundation volume went from 23 cubic kilometers to 30 cubic kilometers for the end of the century. So if we might model Hurricane Ike in the climate conditions as they occurred, and then model it again with that climate change signal imposed on the boundary as the hurricane develops, then the result ultimately is more flood inundation. And so by inundation, we looked at what was initially dry and how it became wet, and then we calculated either the area or the total volume of water that was in that region. So we saw the same thing for the inundation extent. So basically larger spatial areas being impacted by the end of century for the same storm. And these studies didn't include sea level rise at all. So this is totally due to storm surge. So presumably if we add sea level rise onto this scenario on the right, and then maybe like land subsidence or the development, like the eliminating like marshes and wetlands and all that, like there's so much more we could do. Presumably it would be even worse. So we took all 21 storms that we measured and just kind of computed the differences from end of century to present day. So basically, if you look at red, that means that things got worse as far as storm surge inundation. And if you look at blue, it means they got better. And so there are a few places where things are better or there's less storm surge, but overall, it looks like things are red. So we're expecting more storm surges. And a lot of the places where we're seeing blue, it was actually caused by like a slight track shift when we modeled the hurricane. And I mean, that's true for the red as well, but they don't balance out for sure. And so here's some of the metrics. So these are listed in order of increasing control volume for the present day. So I had the most storm surge or inland inundation compared to the other storms that were simulated. And then we looked at kind of how did they change if we looked at the end of century conditions, and then here's the percent change in this column. So what you see is that, you know, there are a few of the storms where the simulation caused less inundation. And again, sometimes this is just due to track changes. But overall, there's kind of an average increase. And then something interesting that we also found was that it's pretty difficult to predict when you will see the change and by how much. So here, if you look at this column for volume, then it's listed in increasing, and this is all changes. So basically red means we saw an increase, and then blue means we saw a decrease. So we saw the largest increase for Francis. And again, right, you have to be careful because things are not, it's relative to what it was, but like Francis had an increase of 161%. And so what we might expect is that we also saw increases in the corresponding parameters that we typically think of. So like maximum wind speed probably increased for a storm that had a significant increase in storm surge, but like in the case of Francis, that's not true. And so I highlighted a couple like drastic examples where it's like red means that intensity is increasing. So the wind speed increased, the radius increased, the translation speed decreased or intensified because a slower storm causes more surge, and the pressure decreased, which corresponds to like an increase in intensity. So all of these particular characteristics that we typically associate with more surge increased, but then we saw less surge. And then same for Dennis, we kind of saw the opposite effect. All of the things are decreasing or staying the same, but then we saw the amount of surge increase. And again, some of the variability can be due to shifts in the track, but mostly we're learning like, yeah, it's changing and it's difficult to predict how. We looked specifically at those storm surge characteristics in both present day and end of century. So here our storms are ordered in terms of the increasing volume or inundation volume. So again, Ike was kind of the biggest one for the present day. And then we again color coded each of the characteristics. So blue is wind speed, red is radius, translation speed, pressure. And so a darker color means like a more intense characteristic or something we would expect to cause more surge. So if the volume is increasing, then we expect the corresponding characteristics to be increasing. So we'd expect to see wind speed go from light blue to dark blue. And again, it doesn't. And then same for end of century. So this again ordered in increasing intensity or increasing volumes. And then we see it doesn't correspond to increasing wind speeds. And so I would say kind of like the major finding like that we're seeing from this is like storm surge risk isn't directly related to storm intensity. And so I've been kind of interested in looking at this question just because as machine learning approaches are becoming super popular, it seems like this is not a great application for that type of thing. Like it's really hard to correlate the behavior without having some of the physics embedded. So to conclude, I will say that storm surge is a low probability but very high impact hazard. How low of a probability is greatly impacted by expected tropical cyclone frequency, which is uncertain. So if you remember on the plot I showed here, kind of these ones that are reflecting that the storm climatology isn't having as significant of an impact as the other models. This model, Emory, also was predicting lower frequencies for the storms at the end of the century. So higher intensity, but lower frequency. And that's what was keeping this risk down. So how low is greatly impacted by the expected tropical cyclone frequency, which is uncertain. So that's kind of where the models disagree. But how high of an impact the storms have is greatly impacted by a lot of things. So the storms themselves, like tropical cyclone intensity, size, translation speed, and the uncertainties in each. And then other things that are connected to this. So for example, levee failures or structural infrastructure, population density and transportation systems, and then also compound flood events and infrastructure. So, you know, how much rainfall is there and how is that changing is all going to affect how high impact storm surge is now and in the future. So it seems that numerical storm surge modeling is and will remain an essential tool for risk assessment. But I think it's really important to think about the multidisciplinary aspects that come into play when we're really trying to address how to improve coastal resilience and understanding that we really do need multidisciplinary work. And so that is my last slide. So I would be happy to take any questions.
Awesome talk. Thank you so much, Dr. Mayo. To ask questions, we have about 13 minutes, so you can just unmute yourself and ask. You can put them in the chat box and I will read them out, or you can raise your hand and I'll call on you. Go ahead, John.
Thanks, Talea. That was very interesting. When you started out by describing the generalized Pareto distribution, which I've seen in other contexts, and that was a nice sort of framework in which you could look at simply the effect of increased sea level when that statistical distribution stays the same. Am I correct?
Yeah, so we didn't assume that the distribution stayed the same because we modeled the end of century storms too. So we applied the same framework for two sets so that we could look at how was it changing.
So you're actually deducing the changes in those parameters that describe the GPD.
Yeah.
Okay.
So in the paper, like I actually show what they are and how they change. So specifically like the shape parameter basically can tell you if every level is attainable or if there's like some bound. And so I look like pretty closely at how do those actually change it. So if it's like, well, no matter what happens, you're never going to get a surge greater than whatever value, using that type of model can tell you if that changes.
And so this number of 2,000 or 3,000 storms, that from your experiences, the size of the ensemble you need to get a statistically significant difference in those parameters of the GPD?
Yeah, I don't know if I don't know if I would say that. I don't know why we specifically use that because I've seen other studies that use more or less. I think kind of the advantage of what we were doing was we had a lot of samples for a particular place. So we would have like 3,000 samples for present day climate at Norfolk, and then 3,000 samples for future climate at Norfolk. And then we'd model them both and assess like how those changes were. I'm not sure if that makes sense.
Yep. Yep.
But yeah, we
Okay.
didn't assume that the distribution stayed the same.
Okay, thanks.
TJ, go ahead.
Hey, thanks for the talk. It was super interesting. I had a quick question. Were you guys thinking about the impact of dredging in your risk assessments and how like changes in, like, because I know that they were dredging like the Newark Bay Area to accommodate larger container ships coming in. So have you guys thought about how like changes in dredging could impact like the flood risk in certain areas?
Yeah, we didn't account for that in any of the analysis we've done. Like I would say we certainly like understand that this would further impact that. So I call that like geomorphological changes we didn't assess because I guess you could do it crudely with the model we have, but in theory you would apply another model. So I would say it's something that we've thought about, but it's not accounted for in the results we have here. So similarly to like the probabilistic or the deterministic paper where I was saying like you might consider this like a best case scenario, like that's the kind of thing that would make it worse.
Cool, thank you.
Bob?
Oh, hey, Talea, great talk. Really enjoyed it. A lot of interesting things to think about. You had talked about using slosh and using AdCirc, and I just wonder like how, how like if you try to hindcast a specific storm, say Hurricane Sandy with those two models, how accurate are they? How much better is a really good AdCirc model, and what are the biggest uncertainties you see?
Yeah, so I think I heard you say what are the uncertainties? How good are they at like doing a deterministic hindcast? And where are the uncertainties coming from in both or in AdCirc?
In both.
Yeah, so I think that is a tricky question. So I think
it wasn't meant to be tricky, but sorry.
yeah, like the blanket answer is like you can expect them to be reasonable within 20%. That's the slosh number. So there's reports that will show that it's within 20%. In the work that I did some evaluation of that, and that was what I found, more or less, like sometimes 21%, but about 20%. And so it's easier to say that for slosh because it's out the box, right? You're not really able to make a lot of, well, you can, but you need some expertise to make more changes. For AdCirc, it's a lot harder to answer because the meshes aren't standardized. So the mesh that I showed, there was like a whole report about how that mesh performs on specific storms. And what really impacts both models is the wind model within the model. So for slosh, even for slosh, like the paper I have on wind field representation can have a big impact on how good it does. Okay. So I think most people from the surge community would say the biggest source of uncertainty is the wind. And then I would add, it's not just the wind, the way you think like, oh, did you have the right max wind speed? It's also like, how did you represent the profile? So did you use like a parametric wind profile? Did you use gridded data? But I would say that's probably the answer that I don't have to be shy about.
Yeah, that's great. Well, I got a million other questions, but just one other. How about resolution? Is resolution of the ocean model and estuaries really important? And or do you define it as you refine it to some point you've kind of have asymptoted to that?
Yeah, I think it depends on where you're concerned about. So I think if you're modeling away from that, I don't think that the effects of like really good resolution in a particular area should greatly impact your resolution somewhere like upshore. But I think that depends, and that's kind of where the variability in how good is AdCirc comes, because if you need work done for a special place, then you're going to put the extra effort and computational power behind more resolution there. Does that answer what you've said?
Yeah, okay, yeah, sort of, yeah. I'll talk to you after in the chat.
Okay.
Yeah. Thank you very much. Really appreciate it.
Kathleen?
Hi, yes, I was just kind of curious. I really enjoyed your topic and your presentation. I thought it was very well done. I was just kind of curious if you thought that maybe climate change may have a bit of a correlation with the amount of hurricane frequency, if that might affect anything, or like the sea level rise as well, especially with pollutants and everything.
Yeah, I mean, it's not my area, but all of the literature that, I base the stuff that I work on pretty much says that. I saw an interesting, it says that meaning like climate change is going to impact frequency. And I saw a pretty good paper that was talking about kind of the spatial shifts and where and how like we would expect to see more things on the East Coast or north of like some latitude, and I can write your name and follow up with that paper. But certainly, and then I think that's really what controls, it controls a lot as far as the return curves or the 100-year flood that you expect. It has a lot to do with the frequency.
Malin?
Yeah, thanks, Talea. Really cool talk, and I like the way you broke it down for those of us who aren't numerical modelers. It could have been happening on my end too. I was wondering about that link between the climate change effect and the decrease in return times. And you showed initially that there's this larger fraction of large radius storms and also this shift towards higher wind speeds. And I was just wondering are those the two main climate change mechanisms that are influencing the shorter return time of the big storm surges, or are there other key changes in the natures of these storms that also contribute to that much lower return time? I was wondering if you thought through that.
So initially, when you just asked that, I was thinking of like the kind of rainbow plots I was showing where we looked at the specific parameters that are supposed to influence the storms and how we showed like they really don't the way you expect.
Exactly.
But when I guess like the probabilistic approach has another layer of model, because once we get those surges, then we're pushing them through this Pareto distribution. And so when I think about that part, then I don't know. Like I don't know what's the sensitivity of like those curves to each of those parameters. But all of I showed numbers, or I showed the plot here for the radius of maximum wind and max wind speed, but all of the changes are reflected through the methodology because the hurricanes are generated. So yeah, I don't know. Yeah.
Thanks.
Chris or Kathleen, did you have another question, or is your hand just still up?
Sorry, I forgot to put my hand down. My bad.
All good. Just checking in.
Same.
All right. Well, any last questions for our speaker? Go ahead, Bob.
Yeah, it was interesting in one of the plots. I couldn't help but noticing, since I work in estuaries a lot, that you showed an increase in Delaware Bay, but not in Chesapeake Bay.
Okay.
Like I know Delaware Bay was red and Chesapeake Bay wasn't. Yeah, and so you think is that storm track?
Yeah, so it's because it's deterministic modeling, so it's not. I think I like this plot, but it does have to be explained. It's just we took one storm and then another and looked at what was the difference in surge.
Oh, I
so
see.
If we don't have a storm that affected that area, then you don't see it.
Mm-hmm. Gotcha. Okay, thank you.
All right. If we could thank our speaker one more time. Some virtual round of applause. We also have a post-seminar happy hour Zoom room for a more casual conversation. I just put that link in the chat, so we hope to see some of you there. And I'll also send it to the DMCS all email listserv. All right, everyone have a good evening.
Thanks, everyone.
Thank you.
Thank you. Very nice.